if R and S are congruent mod n. If and only if R is congruent to S mod little n. In other words, the order of this element. Okay, that's what we have to prove. All right, as usual, call this statement P. Call this statement Q. Now it's if and only if. So P, if and only if Q. So as usual, start with the if statement. Let's see. So P if Q. So P is true if Q is true. Okay, so start with Q. Well, therefore you can deduce P. So in other words, go from the right-hand side to the left-hand side. So we start with this. This is given. And we have to prove these two are equal. Okay? Let's see. So you start with R and S being congruent, mod n. You know that. So by definition, so R is congruent to S mod n. So that means that n, little n, divs R minus S. Okay, that's the definition of two congruent numbers. If mod n, that means that n divides R minus S. Okay, so that means this R minus S you can write in the following form. So R minus S is some integer k times n. Right? See, if n divides R minus S, then n is a factor of R minus S. So if n's a factor, there's some other integer here. So you know that. All right. So that means you can. So therefore R, just take the S over the other side. So little r is S plus kn. Right. All right. So we're starting with the right hand side. Now we need to prove that x to the r is equal to x to the s. So let's work on x to the r. Well, we know r is this form, okay? So that's of the form x to the s plus kn. Right? Now we can split this up. This becomes x to the s times x to the kn. Right? And we can rewrite this a little bit. So that's x to the s, and this will be just change the order of these two, kn to nk, and you'll see in a minute why I'm doing that. So I can rewrite this as x to the n to the k. Okay, same thing, but look, x to the n is the order, it's e. So this just becomes x to the s, e to the k. Now e to the k is just e, and that's just x to the s. Right? So we'll just start here. Yeah, x to the r equals x to the s. So we've proved the left hand side. I mean, we've derived the left hand side. So we've done the if part. Okay, the only if. Right, now we start with the left hand side. We have to derive. So now the only if part, the only if. That's so p only if q. The only way you get P is if you got Q. So if you do have P, you must have had Q. So if P, then Q. So P, then Q. Alright, so P is the left-hand side. So we start with this. X to the R equals X to the S. And we have to show that R and S are congruent integers. All right, how to proceed? Well, let's use, done this kind of thing several times already. Let's use the division, I think that's right. Let me just check here. Oh, well, there's a quicker way. What I was just saying, to use the division algorithm, that was part of a previous proof. So let's just take the result and use it, right? So if x to the r equals x to the s, then x to the r minus s is just e, right? And from theorem 17, so the previous theorem, if this is true, then r minus s, so then little n, the order, divides this, divides it. Now we proved that theorem a few lectures back, so have a look around, what's page 44, page 44, theorem 17, page 44 in your textbook, if you're using your textbook, okay? So so here's what the theorem 17 says. If x to the n equals e, then little n, the order of x, divides big N. Okay? So here your big N is just r minus s. So little n, the order of your element x. Okay? So little n divides that. Now, by definition, that means that R is congruent to S mod N. Okay? So we've proven, we have the only if side. So we've done both. We've done the if and the only if, and therefore we've shown this to be the case. And that is part 2. Now, so not only show this, part 2 also says, and it continues on, so the powers of x, the powers of x, let's call it n if you like, repeat in cycles of length n. So here we can use the division algorithm. So let's write space as usual. let's write m in terms of n. So it'll be of the form, I don't know, k n plus r. Right? Now r will be less than n. This the division algorithm. We've done this quite a few times. Right? So r is less than n, greater or equal to 0. And okay, so x to the m, this will be you just put this kn plus r, so kn plus r, and that's x to the nk. I'm skipping a few lines, but x to the r. Okay. Now x, I put a bracket around it, so that's just e, right? Because it's the order of x. So x to the n is just e. So e to the k is still just e. So you're just left with x to the r. And look, r is less than n. Okay. So this power, as it keeps increasing, and goes up to infinity, is always of this form. And so this is equal to r. Right, that's equal to r. Now r is less than n. So as this goes off into infinity, you're looping, and it'll go like each time here, as your k increases by 1, this number here has increased by n. Okay, so you'll keep getting this value x to the r as k increases by 1. So as the power increases by n, little n. Follow that? Follow that? So as you go through n, as n increases by n, so if x to the m is x to the r, then x to the m plus n, so you increase your k by 1, and you'll still get x to the r. So it's cycling. You're getting the same value after every power, every time you add an n here. So if you add an n here, this k will go up by 1. Right? So it's cycling, and the number of how can I put this? The cycle length, if you like, is n. Does that seem sort of intuitively obvious? All right. Now, the reason I'm emphasizing that is because we're going to use that in Theorem 36. Okay. So just take a sort of mental note. When the order of an element is finite, and let's say it's n, little n, that's its order of the element. Okay. Then if you take x to any power, it will cycle. So x to the n equals x to the r, and r, little r here, is less than the order of your x. Okay. So it'll cycle, and the period, if you like, I mean, how long is the, what can I call it? The repeat length, if you like. It'll be n, right? So, for example, if the order of an element is, I don't know, say 4, then every fourth power you'll get a repeat. This one will keep repeating every fourth power. Okay. All right. So that's theorem 18. Now I can jump back to where we were. So if in the future I need theorems 19 and 20, which I skipped, in an earlier lecture I skipped 3 actually, 18, which I've just now done, 19 and 20, but we need 18 for now. So if in the future lectures I need theorems 19 or 20, well, I'll just do them then, if, as the need arises. Okay. Theorem 36. I need the board, so perhaps I should stop just for a moment.